In this video, we want to look at the determinant of a product. Now, we're not going to get all the way to what the determinant of a product is, but we're going to get ourselves started, and in the next video, we'll finish that process. So here we go. We're going to start with a lemma. Now, a lemma is a theorem, but a lemma is a theorem that's only used is to help you prove another theorem. So anyway, in itself is not necessarily important, but it's useful in proving other things. So here we go. If B is an n by n matrix and E is an n by n elementary matrix, then the determinant of E times B is, in fact, the determinant of E times the determinant of B. This is what I'm after eventually for the whole thing, that the determinant of a product is the product of the determinants. But at least for an elementary matrix, I'm going to be able to show that it works. And really, the proof of this is stuff we've already done in realizing that multiplying by an elementary matrix on the left performs a row operation, right? There's three types of elementary matrices. There's three types of row operations. And the corresponding elementary matrix does that row operation. So I just have to look at the three different types of things. For instance, if E is something like this, where you've taken an identity matrix and multiplied one of the rows by a constant k, then, well, first of all, the determinant of E is equal to k, and E times B is just a matrix that you get when you start with B and multiply the same row as you did here by k. Well, multiplying a row by k is going to change the determinant by a factor of k. Right? So right down here, the determinant of E times B is just going to be k times the determinant of B, because you just multiplied a row of B by k. But k is the determinant of E, so the determinant of E times B is the determinant of E times the determinant of B. Okay. Likewise, if E was just a row swap away from the identity, then multiplying E times B is going to be swapping the same two rows of B, and swapping two rows of B is going to change the determinant by multiplying by -1. So hence the determinant of E times B is minus the determinant of B, but E was just a row swap away from the identity, so its determinant is equal to -1, and the determinant of E times B is -1 times the determinant of B, which is exactly this, det E times det B. Okay. And then for the last type, I didn't even write it down here, but it's the same idea. If E is a matrix where you've taken an identity and added a multiple of one row to another, then the determinant of that matrix is still 1. And if you multiply that matrix times B, then you're just going to add a multiple of one row of B to another row of B, and its determinant would stay the same. So anyway, you multiply it by 1, and then you get the same thing. Right? And notice now that if this worked just E times B, then it actually is going to work for any finite product, because you can say, oh, this is just E1 times all of this stuff, and you can peel off the E1 times the determinant of everything that's left. But then you can say, oh, but wait, this is an elementary matrix times all of this stuff. And so you can one by one peel off these determinants of an elementary matrix out in front till you just get down to B at the end here. So a finite product of elementary matrices with another matrix, take the determinant, that's the determinant of each of the elementary matrices times the determinant of that B. Okay. This actually gives us a very nice theorem that we can prove. In fact, it will end up being equivalent statement to some other ones that we have. So I have here that a square matrix A is invertible if and only if its determinant is not equal to 0. So here we go. Let R be the reduced row echelon form of A, right? So I can write R as some sequence of elementary matrices multiplied by A, because if it's the reduced row echelon form, there was a sequence of row operations that took A into R. Now the determinant of R is, by the lemma that we just had, equal to the determinant of each one of these things multiplied together times the determinant of A. I'll point out that elementary matrices, the determinant is never equal to 0, right? They're either equal to 1 or -1 or k, right? But only when k was not 0. So these are definitely not 0, which tells me that the determinant of A and the determinant of R are either both equal to 0 or neither equal to 0. Right? That is, the determinant of R is equal to 0 if and only if the determinant of A is equal to 0. Which then we can say this: if A is invertible, then we know that the reduced to echelon form is the identity matrix, which tells me that the determinant of R is 1 because it's an identity matrix, and the determinant of the identity matrix is 1. That's not 0. So the determinant of A is not 0. So if A is invertible, the determinant's not 0. Now suppose that the determinant of A is not 0, then the determinant of R is not 0. Since R is in a reduced row echelon form, then it is an upper triangular matrix. And the determinant's not equal to 0, which means there's no zeros on the diagonal. And if there's no zeros on the diagonal, then it must be the identity matrix. And so the reduced row echelon form of A is the identity matrix, and A is invertible. Okay. This is something we're going to use a fair amount. It fits in with our equivalent statements, right? We had a whole bunch of things that were equivalent to saying that A is invertible. Now we have one more thing. A is invertible if and only if the determinant is not equal to 0.